Hi, my name is Ong, and I will be introducing this paper called Understanding by Understanding Not, Modeling Negation in Language Models. This is a relatively recent paper as of today, June 18th. This was a paper that was published in NAACL, the North American chapter of ACL, Conference 2021. And I was thinking, since I did a paper reading sharing at my lab on this paper, I might as well record one just for recording sake. Yeah. So for some of you who might feel like, hey, the name Aaron Colville seems familiar. If you have ever been through Deep Learning, the book Deep Learning, you will notice that Aaron Colville is one of the 3 writers who were in charge of this very good book. And the reason why I'm particularly interested in this paper is because contrary to a lot of the hype that bird can solve a lot of our problems, it's one of the greatest push in language modeling, etc. It does deal with one thing that to me it was surprising, is that bird actually can't handle negation very well, which is seemingly simple thing. Okay, so I will be talking about that in this presentation. So firstly, let's talk about the problem that this paper attempts to solve. So we know that there has been a lot of progress made in terms of having pre-trained language models, and we can fine-tune these models to actually help us solve a lot of problems. However, pre-trained language models cannot understand negation. Okay, so in recent papers, actually as recent as 20, or rather as near to when um, the bird paper was actually published, they already were able to identify that, hey, bird and the pre-trained language models are not able to correctly distinguish between negated and non-negated forms of closed passage fill in the blank tests. So if you look at the example below, if you have an example, the capital of Cuba is mask. The token that will be generated to fill in the mask would be Havana, which is the correct answer, factually correct. However, if you have the capital of Cuba is not mask, the pre-trained language model will still generate Havana. And we know that this is factually incorrect. So the factual correctness is a problem. While both are grammatically correct, but it's not able to keep track of the factual correctness and the negation that happens in this process. Okay, so what is actually being done to solve this problem? The contributions in this paper actually is in 2 aspects. First, unlikelihood training with reference. Okay, I need to emphasize the with reference because this is not the first time unlikelihood training is actually being created and used, but it's a new training paradigm for this particular task. However, to actually leverage the benefits of this unlikelihood training with reference, there's a need for data. And so how are we going to get a whole parallel corpus of factually correct statements and their negated statements? So what this paper also did was to come up with a method, an augmentation scheme to automatically generate negated sentences. Okay, so we will talk briefly about the unlikelihood training in reference first. Okay, so what is unlikelihood training with reference? So basically, we know that during the fine-tuning process, what will be fed into the pre-trained language model for fine-tuning purposes is in the format of sentence A and sentence B, where A is the factually correct sentence and sentence B will be the so-called negated sentence. In this case, then the A sentence, the factually correct sentence, provides the grounding, or the reference of truth for sentence B. Okay, so why are we using unlikelihood training with reference? Did the paper authors not try to use unlikelihood without reference? Apparently, they actually did try, but as expected, it performed poorly for both data sets that they worked on. At this point, I would like to confess I do not understand why they say as expected, because I'm not particularly familiar with the technical situation. Okay, but then let's go a bit deeper and look at what unlikelihood training is. So unlikelihood training, if you look at how the loss is actually defined, we actually first in the middle of it have 1 minus the probability of the token U given the previous utterances. Okay, so this is actually opposite to what we normally know. Because usually what we are looking for is the probability of a particular utterance given the previous utterances. Okay, so this is actually flipping it around, and therefore we call it unlikelihood. The question is, why was unlikelihood training actually created? The truth is, pre-trained language models and language models had this problem of repeating certain utterances. Okay, so a very simple example is, some sentences can go on and on forever. For example, I like apple and pear and apple and pear and apple and pear. And to prevent this kind of thing from happening, you need to sort of reduce the likelihood of utterances that have appeared before. So I like apple and oranges, and then at this point you would say, oh, apple has already appeared. Therefore, it's going to be very unlikely that we're going to see apple again. So that's what unlikelihood is for. Okay. On top of unlikelihood training, there's also this part where the paper authors use knowledge distillation laws to also guide the fine-tuning process. So what is knowledge distillation laws? Simply put, knowledge distillation is actually a recent way of training or rather distilling knowledge from a teacher to a student in a deep neural network. So basically we have very big, very deep neural networks, and you want to put them into a smaller sized language model, okay, which would work faster and which would work almost as well. Okay, almost 90+% as well if we're talking about, for example, Distillbird, which is one of the more prominent distilled models. So then the question is, there's this distillation loss. What is this distillation loss? You can see this definition here. Distillation loss uses the soft targets to minimize the squared difference between the logits produced by the cumbersome model and the logits produced by the small model. So what is this logits thing? Is basically the input being fed to the final layer, where the softmax function, logits are the final inputs to the softmax function before you get the final output. Okay, so what is this soft target thing? So soft targets basically just means, you look at this formula, you would find it very familiar. Simple. Softmax would have been exponential zi over sum of all exponential zj. However, in this case, there's a divided by t over here. This t is called temperature. And by varying this number t, where 1 is obviously the hard default, if you increase it to 2, 3, 4, you can make the whole measurement of this softer, meaning that the probability of a final answer is more fuzzy and softer. Okay, so I'm not going to go into very deep detail of the knowledge distillation loss. Just know that if you go in that direction, you'll be able to find more details on it. I would like to go on to talk about the next thing, which is, so how are we then going to fine tune the pre-trained language model? So obviously you have the unlikelihood training, okay, and you would have to use the positive sentence as the context for the unlikelihood prediction task to ensure that the negated sentence is actually false, and then feed it into the pre-trained language model as a fine-tuning input. But we do have a problem. Where are you going to find that much data? Okay, so what this paper actually also contributed is this method called the syntactic negation augmentation. This whole chunk here is actually from the paper, but to put it very simply, for each sentence that they actually get from their knowledge-based sources. Okay, they would get the input such as the dependency path, the POS tags, morphological info, and then they have some rules based on a dependency tree regex. In this case, they're using semgrex. And then through that, once they identify the corresponding parts, they will perform 4 transformations: move, replace, insert, lemmatize. Okay, so based on the dependence tree regex, what they found in their data is that for 930 sentences, the majority of the sentences match the simple past pattern, etc. Okay, this is just good to note. More specifics on the whole process, you can actually see the semgrex regex here. The pattern is over here. And after it has identified what it needs to identify, it looks at the type of action it needs to take, what is the relative token, etc. And basically from many fonts then made the right leg vertical, it becomes converted to many fonts then did not make the right leg vertical. Okay, specifically what is the code behind this augmentation process? I'm not able to explain in detail at this point. It was not included, but I think there's a general gist that we can understand here. Now, the thing about it is you might think, what's so challenging about creating negative sentences? Isn't it just putting in a not? That is not exactly true. So for example, we have another sentence here. Nowhere in his confession did he mention the Monteagle letter. And in this case, the transformation required is actually just to delete the NPI word nowhere. And once you delete that, in his confession, he did mention the Monteagle letter. So not only do you have to worry about whether the factualness of the negated sentence is correct, you also have to worry about whether the um, conjugation is actually accurate and grammatically correct as well after you perform the negation. So that actually makes it a bit challenging. Now, looking at all these example sentences, this is a sample of the sentences that the augmentation process was able to create. And we see that most of the sentences actually came out quite well. For example, the tournament helped demonstrate the high caliber of play in women's soccer versus that tournament did not help demonstrate the high caliber of play in women's soccer. However, as mentioned in the caption over here, examples 5 and 6 are actually not conjugated well because, for example, number 5, when Arjuna was fighting Karna, the latter's chariot's wheel sank into the ground. And we see that the word sank was actually retained in the negated sentence. When Arjuna was fighting Karna, the latter chariot's wheel did not sink into the ground. So there's some problem here. Okay. Another one is on number 6. In this case, the word is it also does not prohibit or restricts the use of certain accounts held at financial institutions. In this case, the singular plural agreement here is actually broken. Okay, but generally we would say that it performed pretty well enough for them to leverage this as the source of all the the fine-tuning data that they required. Okay, so following this, what we are going to actually look at is the data set that they used, and then we'll look at the results. In terms of the data set, they performed experiments, okay, to test whether what is the efficacy, how good, how accurate is this model, which by the way, they have named as BERT not, okay. Um, so BERT not was actually, of course, fine-tuned, and then they perform experiments on LAMA and negated LAMA. So what is LAMA and negated LAMA? LAMA is language model analysis. Basically, it's comprising facts that are either subject relation object triples or question answer pairs. And they are then converted into a closed statement used to query the language model for a missing token. And it's actually, of course, collected from many places, including Google RE relations, such as place of birth, date of birth, place of death, T-Rex, subset of Wikidata, big triples with 41 relations, ConceptNet, Squad, and yeah, that's about it. Okay, so LAMA and negated LAMA. Of course, negated LAMA comes from LAMA that has been switched over to negative sentences. Now, the experiments that were carried out, first, they fine-tuned the pre-trained BERT with a new unlikelihood objective and a knowledge distillation objective, which I have introduced before. Next, they will test the model on the negated LAMA set, which is a negated version of the knowledge probing dataset LAMA introduced in this 2019 paper. They also fine-tuned BERT on another task, okay, which is a language inference task. We will look at that in detail later, but let's look at the negated LAMA dataset experiment results first. Now over here, we see two tables. The top table is the experiment being run on LAMA, and the bottom table is the experiment results after being run on negated LAMA. So if we look at the top table, what is interesting to note is that BERT naught, which is the result of this particular paper, actually has relatively similar results. It's not too far off. This is interesting because we obviously fine-tuned the model for negation, and it is important that even when sentences are not negated, it still understands them perfectly. And we see that that is the situation. It is not the ability to understand non-negated sentences is not affected. Okay, in fact, it might even be improved in some of them. Okay, and this is the measure for this LAMA that's not negated. As for the bottom table, okay, note that the numbers don't match because they are using different metrics. The bottom table uses the mean top one error metric. What is meant by the mean top one error metric? So for example, iOS is developed by obviously Apple, but iOS is not developed by, okay, it's supposed to say either Google or Microsoft. The interesting thing is that we only care about the top choice because obviously that is what the model is going to generate for us as the answer. And that is what it means to have the mean top one error rate, whether the top choice is correct or wrong. And obviously in this case, BERT has made the wrong choice. It assigned the same probability to Apple as it did in the non-negated sentence, as it did in the negated sentence. So that's bad. But if you use BERT naught, okay, Apple, the score for Apple is actually reduced to the extent that it's no longer the first top choice, and Microsoft and Google both come out ahead instead. And in this case, this is actually accepted as a appropriate choice. Okay, so that's how the metric works, and you would see that BERT naught outperforms on every single data subset in terms of identifying and filling in factually correct responses for the negated sentence template. Okay, it is also interesting to note that these are results achieved without direct training on LAMA queries. Okay, so we had pre-trained on another set, and then this was just a test. Okay, so as I previously already told you about the metric, why is it important and how do we actually evaluate the task? You can see it very clearly here. With BERT, you're gonna get this very similar high probability and therefore words being chosen in the top choice for both non-negated and negated sentences. And that is bad. BERT naught avoids that problem. Another task that the paper actually worked on was natural language inference. So what is natural language inference? Basically, we are talking about whether logically a statement follows a previous statement, in which case we will call it entailment, or if the one statement does not follow the previous statement, and therefore we call it non-entailment. And if you look at the specific example, it's quite clear. For example, it does not use the first day of the first month of the Lunar New Year as the start of the Chinese New Year. This is a premise, and the corresponding hypothesis is the Chinese New Year's Day falls on the first day of the first month of the Lunar New Year, which we know does not logically follow. Okay, So since it does not logically follow, the truth label over here, T, column T is truth labels, B is but, Bn is but not. We see that the truth label is non-entailment. However, but not able to detect the negation identifies it as entailment, whereas but not correctly identifies it as non-entailment. Of course, there are definitely not so perfect performances. For example, if you look at example 5, example 6, in those two cases, in fact, not just those two cases, as number 4 as well, um, you would see that but had the upper hand on those particular examples. Nevertheless, from overall point of view, we do see that when negation is involved, but not generally performs better, as seen on the table for above. Okay, so it's actually quite significant, especially the large improvements are on the negated splits in low resource setting, namely the RTE column, whereas for SNLI and MNLI, it's not so high. So to conclude, um, the unlikelihood objective with a reference-based setup for input sentence to model negation can be considered as a pretty successful attempt to resolve to model negation. It allows also the utility of generic sentences and to negate them with a data augmentation method used to be used as examples for the unlikelihood objective. Okay, and last but not least, the results are significant. We see that there's improvement on the error rate on a negated LAMA set while keeping the same performance on the original LAMA queries. We see large improvements on the negated splits in the RTE, but slight improvements only when it's high resource setting, such as SNLI and MNLI. Okay, overall, I think it's a very interesting read, and I think it's a pretty cool paper. That said, there are many other papers that talked about similar problems, such as negated and misprime probes for pre-trained language models. These are preceding papers that actually talked about the negation problem. So if you are interested, feel free to check those out. Okay. If there are any comments or questions, I'm totally open to receiving them on the comment section. However, I do not have the monopoly of knowledge, and it is highly likely that I might not be able to answer you, but nevertheless, we can exchange opinions and comments and see how we can actually both benefit, right? So thank you for taking the time to listen, and I will stop the recording here.